Our solar system is not the quiet neighborhood we once thought it was. The most brilliant astronomers are currently baffled by at least 15 cosmic puzzles hiding in plain sight. By the end of this journey, you will see our celestial backyard with completely new eyes. What force is pulling objects in the distant dark, and why does a perfect hexagon rage on Saturn? How much do you truly know about the place we call home, far beyond the last official planet, in the deep freeze of the Kuiper Belt? A cosmic detective story is unfolding. Here, in the realm of icy leftovers from the solar system's birth, astronomers have spotted something deeply strange. A handful of distant objects, small worlds like Sedna, are not moving as they should. Their elongated orbits are tilted, clustered together in a way that defies the gentle pull of the known planets. It is as if an unseen hand is gently herding them, a persistent gravitational whisper from the dark. This is the first great mystery, the compelling case for a phantom world, a hidden giant we call Planet 9. The evidence is entirely circumstantial, written in the paths of these far-off wanderers. Astronomers Konstantin Batygin and Mike Brown, studying the odd orbital dance, concluded that the simplest explanation is a massive, undiscovered planet. Batygin has said the evidence points to something out there sculpting these orbits. This hypothetical world is not a small rock. It is thought to be a super-Earth, up to 10 times the mass of our own planet, tracing a vast, slow ellipse around the Sun that takes perhaps 20,000 years to complete. We are not seeing the planet itself. We are seeing the footprints it leaves in the snow of the outer solar system. Finding it, however, is a monumental challenge. At such an incredible distance, it would catch only the faintest glimmer of sunlight, making it a billion times dimmer than the planet Jupiter. Our most powerful telescopes must scan vast, dark swaths of sky, looking for a single, slow-moving pixel of light against an endless backdrop of stars. Several surveys are on the hunt, methodically ruling out patches of the predicted orbit, but the search is like looking for a single black marble in a football field at night with only a faint flashlight. What would it mean if we found it? The discovery of Planet 9 would be more than just adding a new line to a list. It would force a dramatic rewrite of our solar system's origin story. How did a planet that big form so far from the Sun? One thrilling possibility is that it did not form here at all. It could be an interstellar vagabond, an exoplanet captured by our Sun's gravity in its chaotic youth, making our solar system a cosmic foster home. Whether it is a native or a captured guest, this ghostly world represents a fundamental gap in our celestial inventory, a silent titan whose gravitational signature teases us from the shadows, keeping the spirit of exploration and discovery alive in our own cosmic backyard. While the hunt for a hidden world continues in the dark, another mystery presents itself in brilliant, swirling color. High above Saturn's north pole, a perfect geometric storm rages. The Cassini spacecraft, during its long mission, sent back images that left scientists speechless, a hexagon of clouds so precise it looked engineered. This is not a fleeting pattern, it is a permanent fixture, a six-sided jet stream wider than 2 Earths placed side by side, and it has been spinning there for at least 4 decades, perhaps far longer. In a universe of swirling spheres and chaotic storms, this polygon is an astonishing violation of expectation. Our own planet's weather is a masterpiece of beautiful chaos, with cyclones that form and dissipate, jet streams that meander. Saturn's hexagon, by contrast, is a monument of eerie order. Planetary scientists who create complex models of atmospheric flow have struggled to make a virtual Saturn produce such a thing. The best theories suggest it could be a giant standing wave, like a note held in the atmosphere's deep fluid, created by differences in wind speed at various layers. It is as if the entire north pole of Saturn is resonating, vibrating at a frequency that manifests as this impossible shape. This persistent polygon is more than a curiosity, it is a laboratory. Its very existence tells us that the atmospheric physics of gas giants operate on a scale and with a stability we can barely comprehend. Understanding why this hexagon forms and persists could unlock secrets about the flow of energy deep within Saturn, where pressures crush matter into strange forms. It stands as a stark, beautiful reminder that the laws of nature can paint with a geometry we never anticipated, proving that other worlds are not just variations of our own, but realms with their own profound and alien rules. From geometric storms we travel to a world of fire, where the very ground is alive. Jupiter's moon Io is a vision of cosmic violence, a place where volcanoes erupt not with rock and ash, but with fountains of molten sulfur that paint the sky yellow and orange. This is the most volcanically active body we have ever seen, anywhere. Its surface is a constantly changing mosaic of black silicate lava lakes and colorful sulfur plains, scarred by hundreds of active vents. Plumes from these eruptions shoot hundreds of kilometers into the thin, poisonous atmosphere, a spectacle of raw planetary power. The source of this inferno is not a hot core, as on Earth, but a relentless gravitational massage. Io is caught in a perpetual tug of war between the immense gravity of Jupiter and the rhythmic pulls of its sister moons, Europa and Ganymede. This gravitational flexing, called tidal heating, stretches and squeezes Io's interior like a ball of clay, generating tremendous friction and heat. But here lies the profound mystery. The models of this tidal heating, while brilliant, struggle to fully explain the ferocity we observe. One planetary geologist put it starkly: Io's heat flow is an order of magnitude greater than Earth's. It is a world turning itself inside out. The puzzles multiply when you look closer. Why are some regions of Io absolutely covered in volcanic calderas, while others are relatively quiet? What is the exact recipe of molten rock and sulfur churning in its mantle that allows for such explosive, continuous activity? Io is more than a celestial curiosity. It is a natural laboratory for extreme geology. By studying how this moon melts itself from within, we are forced to refine our understanding of tidal forces, forces that also shape the hidden oceans of Europa and the cracked surface of Enceladus. Io screams a fundamental lesson that the quiet, cold moons we see from afar can harbor furnaces of unimaginable energy, all powered by the silent, rhythmic dance of gravity. The search for life often begins with the search for a single molecule, and on Mars that molecule is methane. On the cold, dusty plains of the Red Planet, robotic explorers have been sniffing the thin air, and what they have found is a maddening puzzle. Both orbiters and rovers, like Curiosity in Gale Crater, have detected sporadic, fleeting whiffs of methane gas. In our own world, the vast majority of methane is produced by living things, from microbes to livestock, making it a compelling biosignature. On Mars, its presence is a shout in an otherwise silent desert, a signal that something is happening right now. The central conundrum is brutal in its simplicity. The Martian atmosphere is bathed in harsh ultraviolet light from the sun, which should break methane molecules apart within a few hundred years. Finding any methane at all means we are not smelling an ancient relic, we are detecting a leak from an ongoing, hidden source. It is as if you walked into an abandoned, sealed room and caught the faint, fresh scent of bread baking. The oven is still on somewhere. Mission scientists are deeply divided on what that oven could be. The most thrilling possibility is a biological one, that deep beneath the frozen soil, in isolated pockets of briny water, Martian microbes are quietly going about their metabolism, producing this gas as a byproduct. A second, more sober explanation points to geology, a process called serpentinization, where certain rocks react with water, can produce methane abiotically without any life involved. A third idea suggests the gas could be slowly seeping from ancient, icy deposits called clathrates, trapped underground for eons and now releasing their store in tiny bursts. Each explanation paints a radically different picture of Mars. Is it a geologically dead world with fleeting pockets of chemistry, or is it subtly alive? The technical challenge of solving this is immense. Measurements from orbit have to account for the incredibly thin Martian air, while rovers on the surface can only sniff their immediate surroundings. The European Space Agency's Trace Gas Orbiter, designed specifically for this task, has often found the atmosphere mysteriously clean, deepening the mystery of where the rover's detections are coming from. This inconsistency itself is a clue, pointing to a source that is not global, but local and sporadic, perhaps even seasonal. Every tiny spike in the data sends ripples of excitement through the scientific community, because this elusive gas does more than hint at chemistry. It keeps the most profound question of all alive. Is Earth truly alone in its ability to craft the simple, telltale molecules of life? The methane of Mars is a whisper we are still learning how to hear, a faint signature that ensures the red planet remains, in our imaginations and in our science, a world of enduring possibility. The faint whispers of Martian methane speak of hidden processes, but history records a moment when the solar system shouted. In the early morning of June 30th, 1908, over a remote Siberian forest near the Tunguska River, the sky tore itself apart. A fireball brighter than the sun streaked across the heavens, followed by a series of thunderous blasts that knocked people off their feet hundreds of kilometers away. When investigators finally reached the epicenter years later, they found a scene of breathtaking, eerie devastation. Over 2,000 square kilometers of ancient forest had been flattened, millions of trees scorched and laid out in a radial pattern like matchsticks, all pointing away from ground zero. The explosive force is estimated to have been nearly 200 times more powerful than the atomic bomb dropped on Hiroshima. Yet, at the very center of this unimaginable blast, there was no crater. The ground was scarred and burned, but intact. This absence is the heart of a century-old mystery. What exactly was the Tunguska object, and where did it go? For decades, the leading theory pointed to a stony asteroid, perhaps 60 meters across, that entered Earth's atmosphere at a shallow angle and detonated in a massive airburst several kilometers above the ground, its kinetic energy converting instantly into a devastating shockwave. The lack of a crater and the pattern of the fallen trees support this idea of a mid-air explosion. But the puzzle deepens with the lack of any significant meteorite fragments. This has led other researchers to propose a different culprit, a small comet composed of ice and dust. Such a fragile body could have disintegrated completely in the atmosphere, vaporizing entirely and leaving no solid remains, explaining the clean blast zone. The debate grows even more intriguing with fringe yet scientifically considered hypotheses. Could it have been the passage of a tiny, primordial black hole through our planet? Or perhaps a chunk of antimatter annihilating itself upon contact with our atmosphere? While these exotic ideas are far less likely, their very proposal underscores how thoroughly the event defies simple explanation. Modern science continues to sift the evidence. Analysis of soil and tree resin from the site has found microscopic particles rich in elements like iridium and carbon, which could be the vaporized remains of the object. The distribution of these particles and the precise orientation of the fallen trees are still studied today, offering clues to the angle, speed, and composition of the intruder. The Tunguska event is not merely a historical curiosity. It is a stark warning shot across our planet's bow. It demonstrated with terrifying clarity that an object from space does not need to strike the ground to cause continental-scale devastation. A similar airburst over a populated area today would be a global catastrophe. This single mystery, therefore, connects directly to our survival. It forces us to acknowledge a critical gap in our knowledge. We still do not fully understand how different types of asteroids and comets behave as they scream through our atmosphere. Are they solid rock, fragile rubble piles, or icy conglomerates? Their response to atmospheric entry dictates whether they impact, airburst, or simply disintegrate. Solving the Tunguska Enigma is about more than labeling a historical event. It is about calibrating our planetary defense, teaching us what to look for in the dark and what truly constitutes a threat from the sky that gives no second chances. But a world spared from impact still depends on the warmth of its star, and here our own history holds a profound contradiction. 4 billion years ago, our sun was a different star, younger and significantly dimmer, shining with only about 70% of its current brightness. By all the straightforward rules of climate, this faint young sun should have left the early Earth as a permanent, glittering snowball, a global ice age from which life might never have emerged. Yet the geological record tells a defiantly different story. Ancient rocks, some of the oldest on the planet, bear the unmistakable signatures of liquid water, of rivers and oceans, and fossil evidence suggests simple life was already stirring. This is the faint young sun paradox, a glaring mismatch between the energy we know was arriving and the temperate world we know existed. How did Earth stay so warm under such a cool star? Climatologists and planetary scientists have spent decades piecing together a solution, and it paints a picture of a primordial Earth that was a far more extreme, insulating place. The leading answer lies in the air itself. Our planet's first atmosphere was likely a dense, soupy mix, rich in powerful greenhouse gases like methane and carbon dioxide, perhaps hundreds of times thicker than today. This gaseous blanket would have acted like a planetary parka, trapping the sun's meager heat with spectacular efficiency. Another factor could have been the planet's face, its albedo. With less land exposed and different cloud compositions, the early Earth might have absorbed more sunlight instead of reflecting it back into space. This puzzle does not belong to Earth alone. Our neighbor Mars, now a frozen desert, also shows clear geological signs of a warmer, wetter youth, with valley networks and mineral evidence that liquid water once flowed freely. Solving the faint young sun paradox is not just an exercise in ancient history. It is a key to unlocking the universal principles of planetary habitability. It forces us to ask what combination of atmospheric composition, planetary geology, and stellar evolution creates a stable cradle for life. This cosmic riddle elegantly connects the slow brightening of our star to the very first whispers of biology on our world, reminding us that a planet's climate is a fragile, dynamic balance, one that we are only beginning to understand for worlds beyond our own. The faint young sun paradox reveals a world precariously balanced for life, yet that life depends on one vital substance. Look at our planet from space, a stunning blue marble awash in oceans, and a profound question emerges. Where did all this water come from? The sheer volume is staggering, over 330 million cubic miles of it, covering 70% of the surface and carving the very continents. For decades, scientists have debated two competing origin stories, a cosmic tug of war between what was here from the start and what arrived later. The first theory suggests an endogenous origin. In this view, the building blocks of Earth itself, the ancient dust and rocks that coalesced 4.5 billion years ago, already contained water locked away in their mineral structures. As the infant planet grew hotter from collisions and radioactive decay, this water would have been sweated out through volcanic activity, a process called outgassing, slowly filling the basins over eons. The second, more dramatic theory points to an exogenous delivery. This story involves the chaotic era known as the Late Heavy Bombardment, a period around 4 billion years ago when the inner solar system was pummeled by countless asteroids and comets. These icy messengers from the cold outer reaches could have crashed into Earth, delivering their water cargo in a celestial rain that filled our nascent oceans. To distinguish between these possibilities, scientists turn to a kind of cosmic fingerprint, the deuterium to hydrogen ratio. Deuterium is a heavier form of hydrogen, and the proportion of deuterium to normal hydrogen in water varies depending on where in the solar system that water formed. By comparing the ratio in our oceans to that found in different celestial bodies, we can look for a match. Here, the mystery deepens. Samples from comets like the famous 67P, studied by the Rosetta mission, generally show deuterium levels much higher than Earth's oceans, suggesting most of our water did not come from comets like these. Meanwhile, analysis of asteroids, particularly carbonaceous chondrites like those sampled by the Hayabusa 2 mission from asteroid Ryugu, reveals a deuterium to hydrogen ratio that is a much closer match. This points a strong finger at water-rich asteroids as the primary delivery system, yet the puzzle is not completely solved. Some comets from the distant Oort cloud may have different signatures, and the role of the primordial water locked in Earth's mantle is still being quantified. The question of Earth's water is far from a local concern. It is a template for the entire galaxy. When we look at distant exoplanets and assess their potential for habitability, one of the first things we ask is whether they have water. Understanding the mechanisms that delivered water to our own world tells us which kinds of planetary systems are most likely to produce ocean worlds. Was our water a lucky, violent accident or an inevitable outcome of planetary formation in a system with plenty of water-bearing asteroids? The answer shapes our expectations for life elsewhere, making the search for the source of our own oceans a quest to understand our place in a potentially very wet and very living cosmos. Uranus presents a world of serene, featureless blue, but one of its moons tells a story of pure chaos. Miranda is a fractured puzzle, a world that seems to have been shattered and glued back together by a careless cosmic hand. When Voyager 2 raced past the Uranian system in 1986, its cameras captured a moon unlike any other, a celestial patchwork quilt of wildly different terrains jammed violently together. Giant fault canyons, some 12 times deeper than the Grand Canyon, scar its surface. Vast, ridged ovals called coronae sprawl across the landscape like tire tracks from a gargantuan vehicle. There are regions of ancient, heavily cratered ice sitting abruptly beside young, smooth plains, all on a moon barely 500 kilometers wide. This violent asymmetry is the central mystery. How could such a small, cold body muster the geological energy for such extreme and uneven remodeling? Planetary geologists were stunned, as Miranda's small size should have allowed its internal heat to leak away into space billions of years ago, leaving it a dead, frozen relic. The leading theory to explain this jumbled world is as dramatic as its appearance, a colossal impact. The idea suggests that Miranda was once completely shattered by a catastrophic collision with another object. The fragments, over time, slowly recoalesced under their own gravity, but they did so in a haphazard, messy fashion, leaving this geological Frankenstein's monster we see today. The different terrains could represent chunks of Miranda's original crust, its deeper mantle, and slushy material that oozed between the pieces during reassembly. Yet other scientists point to internal forces. Could intense, localized tidal heating from Uranus's gravity, perhaps in concert with its other moons, have created powerful convection currents in Miranda's icy mantle? This might have caused blobs of warmer, buoyant ice to rise to the surface in specific regions, creating the coronae and repaving entire landscapes while leaving other parts ancient and untouched. The small size of Miranda makes either explanation profoundly challenging. An impact violent enough to shatter it might have scattered the pieces forever, while generating enough internal heat to drive such localized geology seems improbable for such a tiny world. Miranda, therefore, is more than a curiosity. it is a fundamental challenge. It forces us to admit that our models for the evolution of icy moons are incomplete, that even small worlds can harbor violent, complex histories we are only beginning to decipher. This fractured moon is a testament to the fact that in the outer solar system, tranquility is often just a mask, hiding a past written in ice and cataclysm. Far beyond the fractured moon Miranda, the solar system holds another boundary that makes no sense. The Kuiper Belt, that vast donut of icy worlds beyond Neptune, does not simply fade into the darkness of interstellar space. Instead, it ends abruptly like a cliff at the edge of a continent. Observations over the past 2 decades have revealed a startling fact. Beyond a distance of about 50 astronomical units, roughly the orbit of Pluto, the population of detectable objects plummets. This is the Kuiper Belt cliff, a sudden and unexplained edge to our solar system's most distant reservoir of ancient ice. According to our best models of how the solar system formed from a swirling disk of gas and dust, there should be no such sharp boundary. The primordial disk was thought to have extended much farther out, gradually thinning. The objects we see today are the frozen leftovers from that era, so finding a hard stop in their distribution is like discovering a library where all the books suddenly end on the same shelf. Something dramatic clearly happened here, an event that either prevented objects from forming beyond this line or violently swept them away. One compelling theory points to a stellar intruder. Our sun was born in a crowded stellar nursery, surrounded by thousands of other young stars. It is possible that in this chaotic early environment, a passing star came close enough to our infant solar system to gravitationally shear off the outer reaches of the Kuiper Belt, stripping away the material beyond a certain radius and leaving the sharp edge we see today. Another, more unsettling idea revisits the ghost of Planet 9. Could the gravitational influence of an unseen, massive planet not only shepherd distant objects into odd orbits, but also act as a cosmic shepherd dog, clearing out a definitive edge to the disk of icy bodies? A third possibility is that our understanding of the primordial disk itself is flawed. Perhaps it was never as smoothly distributed as we assume, containing rings or density waves that led to this uneven fossil record. Each explanation points to a solar system history far more dynamic and violent than a simple, quiet condensation from a cloud. This cliff is not a passive feature. It is a frozen timestamp, a billion-year-old crime scene waiting for its clues to be read. Decoding what caused this edge will tell us not just about the formation of our own system, but about the typical childhoods of stars and their planetary families across the galaxy. Was our solar system's youth a peaceful isolation or a street fight in a stellar neighborhood? The silent, dark wall of the Kuiper Belt cliff holds the answer. Jupiter's face is a masterpiece of flowing bands and swirling storms, but its most famous feature is undergoing a profound transformation. For centuries, the Great Red Spot has dominated the southern hemisphere, a colossal anticyclone so vast it could swallow Earth whole. Yet telescopic observations over the last several decades reveal it is not the eternal monument we once believed. The storm is shrinking, its oval shape becoming more circular, and its iconic brick red hue has faded to a pale salmon, even orange at times. Simultaneously, new, smaller storms, brilliant white ovals, emerge across the planet, sometimes dancing around each other for years before violently merging. This dynamic spectacle presents a fundamental atmospheric mystery. What powers the incredible longevity of these Jovian storms, and what dictates their dramatic evolution? Planetary meteorologists, armed with data from missions like Juno, are peering beneath the cloud tops to find answers. Juno's microwave radiometer allows scientists to see hundreds of kilometers deep, revealing that the Great Red Spot's roots plunge at least 200 miles into the planet's interior, far deeper than any ocean on Earth. This suggests the storm is not a shallow weather feature, but a towering thermal engine, likely fueled by heat rising from Jupiter's seething interior. One researcher described it as a massive chimney, releasing the planet's internal heat into the cold of space. The changing color adds another layer of intrigue. The leading hypothesis links the hue to chemicals being dredged up from deeper layers by the storm's powerful vertical winds. As the storm's dynamics change, perhaps weakening or interacting with other atmospheric bands, the mix of these compounds at the cloud tops shifts, altering the color we see from afar. These giant, persistent vortices are far more than pretty patterns. They are vital windows into processes we cannot directly observe. By tracking their movements, mergers, and transformations, scientists can map the hidden circulation of Jupiter's fluid interior and gauge how energy flows from the deep, hot core out into the cloud decks. The Great Red Spot may be diminishing, but in its slow fade and in the chaotic birth of new storms, Jupiter is actively teaching us. Its evolving face challenges every model of fluid dynamics on a planetary scale, forcing us to reconsider how energy, momentum, and matter interact in an environment without a solid surface, a world where the weather is a direct expression of the planet's fiery heart. Our own moon holds a secret in its gentle orbit, a clue to a forgotten cosmic brawl. It circles Earth at a slight but persistent tilt, roughly 5 degrees off the plane of our planet's journey around the Sun. This may sound minor, but for planetary scientists, it is a glaring inconsistency. The prevailing story of the Moon's birth is the giant impact hypothesis, where a Mars-sized body named Theia slammed into the young Earth. The colossal debris ring from that collision should have settled and coalesced right in line with Earth's equator, giving us a moon with a perfectly flat orbit. The fact that our moon is askew means the story did not end with that single, defining impact. Something else happened in the turbulent aftermath to knock it off kilter. Dynamicists who model the early solar system point to a prolonged era of chaos. After the moon formed, Earth's neighborhood was likely still littered with leftover planetesimals, the building blocks of planets. A few large, subsequent impacts from these remnants could have given the fledgling moon a gravitational nudge, tilting its orbit over millions of years. Another elegant theory suggests a slow, persistent dance with the Sun. As the newborn moon orbited Earth, the Sun's gravity may have gently tugged on its path, establishing a resonance that gradually walked the orbit into its current inclined state. This subtle tilt is far from a trivial detail. It has profound consequences. It is the reason we do not experience a total solar eclipse every single month. Because the moon's orbit is tilted, its shadow usually passes above or below Earth. Only when the Sun, Moon, and Earth align at the precise points where the orbits cross, called nodes, do we witness that breathtaking celestial coincidence. Furthermore, this inclination has shaped the moon's own climate history, affecting how sunlight strikes its poles and creating the permanently shadowed craters where we now hunt for water ice. This 5-degree lean is therefore a fossil, a lasting signature of the solar system's violent youth. It tells us that the Earth-Moon system's formation was not a single, clean event, but a messy, drawn-out process of collisions and gravitational negotiations. Solving this quiet mystery requires peering back through 4.5 billion years to reconstruct a drama of wandering worlds and persistent tugs, a time when our sky was a far more chaotic and active place. While the moon's gentle tilt hints at ancient impacts, another world in our inner solar system presents a spin so bizarre it defies all expectation. Venus rotates backwards. While nearly every planet, including our own, spins counterclockwise when viewed from above the North Pole, Venus spins clockwise in a slow, deliberate retrograde motion. To make this cosmic oddity even stranger, a single day on Venus, the time it takes to complete one full rotation, is longer than its entire year around the Sun. Imagine a world where the Sun rises in the west, sets in the east, and does so only once every 243 Earth days, while the planet completes its orbit in just 225. This is not a minor quirk, it is a fundamental planetary identity crisis. What catastrophic event could have literally flipped a world upside down or brought its spin to such a lethargic crawl? The leading hypothesis is as violent as it is simple: a colossal impact in the solar system's youth. A planetesimal, perhaps as large as the one that formed our moon, could have struck a young, rapidly spinning Venus with such force that it essentially stopped the planet's original spin and set it rotating backwards like striking a spinning top from the side. This theory elegantly explains the retrograde motion, but other scientists point to a slower, more subtle culprit: gravitational tides. Venus may have started with a normal spin and a thick, primitive atmosphere. Over billions of years, the gravitational tug of the Sun on that massive atmosphere, combined with tidal friction from the Sun's pull on the planet's solid body, could have acted as a cosmic brake, gradually slowing its rotation until it stopped and then reversed direction. As one planetary scientist has noted, Venus's spin state is not just a curiosity, it is the engine for its entire alien climate. This bizarre rotation directly drives the planet's super-rotating atmosphere, where hurricane-force winds whip the toxic clouds around the entire globe in just 4 Earth days, far faster than the planet itself turns. This constant global churning helps distribute heat evenly, contributing to the runaway greenhouse effect that bakes the surface at nearly 900 degrees Fahrenheit. Understanding why Venus spins backwards is therefore key to solving the greatest divergence in our solar system: how Earth and Venus, born as near twins in size and composition, could have evolved into such radically different worlds, one a watery cradle of life, the other a scorching, pressurized hellscape. This backward twirl stands as a stark monument to chance, a reminder that in the chaotic construction yard of the early solar system, a single, random blow could forever alter a planet's destiny, locking it into a slow, inverted dance under a hostile sky. While Venus spins its slow, backward dance, another small world performs a far more active spectacle. Enceladus, a gleaming white moon of Saturn no larger than Arizona, hides a secret ocean beneath its icy crust, and it is screaming to be noticed. The Cassini spacecraft's cameras captured something no one predicted: towering geysers of water, ice, and vapor erupting into space from warm fractures near the South Pole, painting intricate patterns against the blackness. These are not random leaks, but a continuous, powerful cryovolcanic eruption, a sign that Enceladus is geologically alive. The plumes themselves are a treasure trove, for Cassini did not just photograph them, it flew directly through them, tasting their composition. The data revealed a stunning cocktail of water vapor, ice particles, salts, and a suite of simple organic molecules, the carbon-based building blocks essential for life as we know it. This was the moment a small, frozen moon transformed from a curiosity into a prime candidate in the search for life elsewhere. The implications are staggering. These plumes are not sourced from a small, isolated lake, but from a global, liquid water ocean that wraps the entire moon, sealed between its rocky core and its icy shell. The presence of sodium and potassium salts suggests the ocean is in direct contact with that rocky seabed, a crucial detail. On Earth, such an interface, heated by geological activity, creates hydrothermal vents, ecosystems that thrive in complete darkness, powered not by sunlight but by chemistry. Astrobiologists speak of Enceladus with palpable excitement, noting it has all the key ingredients: liquid water, a source of chemical energy, and the essential organic building blocks. It presents a nearly perfect laboratory for probiotic chemistry, a place where the steps toward life could be unfolding right now in the eternal dark. Yet for all its promise, Enceladus raises profound new questions. What is the exact mechanism that keeps this entire ocean from freezing solid in the deep cold of space? The leading answer is tidal heating, the same gravitational flexing that torments Io, but here it acts more gently, warming the core enough to maintain a liquid layer. How long has this system been active? Is it a stable feature lasting billions of years, giving life time to emerge, or a fleeting, recent phenomenon? Each pass of Cassini through the plumes provided more clues, but the mission had to end, leaving the most tantalizing questions unanswered. This tiny, brilliant world now stands as a beacon. Its plumes offer something almost miraculous, a direct, free sample of an alien ocean, delivered into space for us to study. Future missions propose not just flying through the spray, but landing near the tiger stripe fractures to analyze pristine ice, or even sending a probe to dive through a vent and into the ocean itself. Enceladus teaches us that habitability is not about a planet's size or its distance from the Sun alone, but about the hidden internal dynamics that can maintain a warm, wet sanctuary against all odds. It is a frozen shell guarding a possibly living heart, a quiet revolution in our understanding of where life could call home. The possibility of a hidden ocean on a moon like Enceladus is a staggering thought, but it forces us to look even farther out, to a frontier so distant it exists only in theory. Our solar system's influence does not end at the Kuiper Belt's sharp cliff. Astronomers are confident that a vast, spherical shell of icy objects surrounds us, a celestial reservoir so far away it defies easy comprehension. This is the Oort cloud, a hypothesized realm of frozen wanderers beginning perhaps 2,000 times farther from the Sun than Earth, and stretching outward for light years. We have never seen a single object from the Oort cloud directly, and no human-made probe will ever reach it in any foreseeable future. Its existence is inferred entirely from the long-period comets that occasionally grace our skies, visitors like Comet Hale-Bopp, whose immense, looping orbits suggest they originate from this unimaginably distant deep freeze. These comets are the messengers, and their paths tell a story of a solar system far larger and more dynamic than it appears. The central mystery of the Oort cloud is not whether it exists, but how it was built. The objects within it are not exotic alien material. They are the same icy planetesimals that formed in the neighborhood of the giant planets like Jupiter and Saturn. The puzzle is explaining how these building blocks, which coalesced relatively close to the Sun, were catapulted to such mind-boggling distances. The leading model is a gravitational pinball machine of epic scale. In the solar system's chaotic youth, as the giant planets jockeyed for position, their immense gravity would have acted like slingshots, violently flinging countless small, icy bodies outward. Some were ejected entirely into interstellar space, becoming rogue nomads. Others, however, received just the right nudge, sent on trajectories so vast and slow that they only reached the outermost gravitational embrace of the Sun, settling into the theoretical shell of the Oort cloud. This scattering process was likely supercharged by the Sun's own early environment. Our star was born in a dense cluster alongside thousands of stellar siblings. The gentle gravitational nudges from these passing sibling stars over millions of years would have helped shepherd these exiled objects into a more spherical distribution, rather than a flat belt, sculpting the cloud's proposed shape. This makes the Oort cloud more than just a storage locker for comets. It is a frozen archive, a billion-strong population of pristine time capsules holding the unchanged chemistry of the solar system's birth. Each long-period comet that tumbles inward is like a page ripped from that ancient ledger, offering us a direct sample of the primordial mixture from which the planets were made. Studying their composition tells us about the conditions in our corner of the galaxy over 4.5 billion years ago. The profound irony is that this most distant part of our solar system, forever beyond our physical reach, may hold the purest and most accessible record of its very beginning, delivered to our doorstep by icy messengers on orbits that span epochs. Our very star, the Sun, holds a chemical mystery in its heart. When astronomers measure the abundance of lithium in its fiery atmosphere, they find a puzzling deficit. This light element, the third simplest in the universe, is curiously scarce in our Sun compared to other stars of similar age and composition. Even more telling, ancient meteorites that formed alongside the solar system contain far more lithium than our star does today. This is not a trivial difference, it is a glaring inconsistency that challenges our fundamental models of how stars live and burn. Standard stellar theory suggests that a star like the Sun should preserve its initial lithium for billions of years, only destroying it deep in the core where temperatures soar above 2.5 million degrees. The puzzle is that the lithium we can measure resides in the cooler outer layers, far from that destructive furnace. So where did it go? How did our Sun manage to burn through this element so efficiently? Heliosismology, the science of studying the Sun's internal vibrations, provides crucial clues. By listening to the star's natural oscillations, scientists can map its internal structure and rotation. The data suggests our Sun may have a more complex and dynamic interior than once thought. One leading theory points to rotational mixing. In its turbulent youth, the Sun may have spun much faster, generating powerful currents and magnetic fields that churned its interior like a cosmic blender. This mixing could have dredged surface lithium down into hotter regions where it was subsequently destroyed. Another idea involves a process called gravitational settling, where heavier elements slowly sink over eons, potentially altering the chemistry of the layers we observe. There is even speculation about unusual nuclear burning processes in the Sun's earliest, most active phase. Each proposed solution rewrites a page in the stellar instruction manual. This missing lithium is far more than an academic curiosity. Lithium acts as a delicate cosmic clock. In star clusters, where all stars are born from the same cloud at the same time, the amount of lithium they retain tells astronomers about their internal dynamics and age. If we cannot account for the Sun's depletion, our methods for dating these stellar families become uncertain. Solving this subtle chemical anomaly is therefore key to calibrating our understanding of all stars. It forces us to peer deeper into the Sun's past, to an era of fierce magnetic storms and violent rotation, to uncover the hidden mechanics that quietly shape the composition of our own life-giving star. The answer, written in that absent element, will refine our picture of stellar evolution itself, ensuring that the engine at the center of our system is no longer a mystery, but a benchmark for the galaxy. Taken together, these 15 cosmic riddles form something far greater than a list of oddities. They are interconnected clues in a single, grand investigation, a detective story spanning 4.5 billion years. Each mystery challenges a different foundational pillar of our science. The faint young sun paradox questions our models of stellar evolution and planetary climate. The backward spin of Venus defies our understanding of planetary formation and angular momentum. The missing lithium in our Sun's atmosphere probes the hidden dynamics of stars themselves. Every strange orbit, every unexplained storm, every chemical anomaly is a crack in the facade of a too simple story, revealing just how much we have yet to learn about the forces that built our home. This is why we explore. Missions are not launched out of mere curiosity, but as targeted experiments to test these very hypotheses. The James Webb Space Telescope peers into the atmospheres of exoplanets, helping us calibrate the faint young sun paradox for other stars. Future Mars sample return missions aim to bring back rocks that could finally resolve the origin of that planet's fleeting methane. Probes destined for the icy moons of Jupiter and Saturn, like the upcoming Europa Clipper, are engineered to sniff out the chemistry of alien oceans and search for the signatures of life. Each spacecraft is a question sent into the dark, designed to pry answers from these silent, distant worlds. The philosophical implication is profound. Our cosmic neighborhood, once charted and seemingly settled in textbooks, has re-emerged as a vibrant frontier. It is a place not of known quantities, but of looming shadows and whispered possibilities. This constant state of mystery is not a failure of science, but its very engine. It drives technological innovation, from more sensitive spectrometers to more resilient deep space probes. More importantly, it cultivates a necessary humility. For every answer we find, like the source of Earth's water in ancient asteroids, a dozen new questions erupt, like the sharp edge of the Kuiper Belt cliff. This endless cycle of discovery and doubt is what keeps our gaze turned upward. These unsolved mysteries are not gaps in our knowledge. They are the very definition of the cutting edge, the glowing perimeter beyond the map that compels us to keep looking, to keep wondering what other astonishing truths are waiting, hidden in the familiar sky. This portrait of a dynamic, violent, and mysterious solar system is not a sign of our ignorance, but a testament to our growing awareness. The 15 cosmic puzzles we have explored are not failures of science, they are its fuel. Each one is a beacon, a bright and unanswered question that guides the next generation of telescopes, spacecraft, and brilliant minds. From the hypothesized giant in the darkness to the missing lithium in our own star, these enigmas define the very frontiers of our knowledge. They are open invitations to wonder, to investigate, and to continually rewrite the story of our celestial home. Every time a probe sails past a distant world or a telescope captures a new frequency of light, we are sending our curiosity directly into these mysteries, peeling back another layer of the cosmos. This ongoing journey reminds us that the universe is not a static museum, but a living, evolving puzzle of breathtaking scale. We want to hear which of these mysteries baffles you the most. Share your thoughts in the comments below. For more deep dives into cosmic curiosities, subscribe and keep looking up.